Hello everyone, our group is Group22 and our team members have Teo Le Xuan, Yap En Tong and Yu Xuan.
Now, let's move on to the circuit schematic. This figure shows the complete RC coupled FET BJT multi-stage amplifier implemented in LT-SPICE. The circuit is powered by a 15-volt DC power supply (VCC). Starting from the input, VC passes through the 600 ohm source resistor R6 and the input coupling capacitor C1 before entering the MOSFET stage. C1 blocks the DC component while allowing the AC signal to pass. In the first stage, RG1, which is 50 kΩ, and RG2, which is 60 kΩ, forms the gate bias network for transistor Q1. The drain resistor RD, which is 4.5 kΩ, develops the output voltage, while the source resistor RS, which is 3 kΩ, stabilizes the operating point. Capacitor C3 bypass RS for AC signals to increase the stage gain. The amplified signal is then coupled through capacitor C2 to the second stage. In the BJT stage, R1, which is 75 kΩ, and R2, which is 9 kΩ, provide the base bias for transistor Q2. The collector resistor, RC, which is 5 kΩ, develops the output voltage. RE1 and RE2 with values of 2 kΩ and 1 kΩ stabilize the transistor, while capacitor C4 bypass RE2 to improve the AC voltage gain. Finally, the output signal passes through the output coupling capacitor C5 to the 20 kΩ load resistor RL, where the amplified output voltage Vout is measured. I will start from the block diagram of our amplifier system, which shows the overall signal flow from the input source to the output load. The input signal V6 first passes through the input coupling capacitor C1, which blocks the DC component while allowing the AC signal to enter the amplifier. The signal then enters stage 1, which is a common source MOSFET amplifier using transistor Q1. This stage provides the initial voltage amplification with a high input impedance. Capacitor C3 acts as a bypass capacitor to improve the AC voltage gain. The amplified signal is then transferred through the interstage coupling capacitor C2, which isolates the DC bias between the two amplifier stages. Next, the signal enters stage 2, which is a common emitter BJT amplifier using transistor Q2. This stage provides additional voltage amplification, while capacitor C4 acts as the bypass capacitor to further increase the AC gain. Finally, the output signal passes through the output coupling capacitor C5 before reaching the load resistor RL, where the final amplified output voltage Vout is obtained. Overall, the two amplifier stages work together to provide a higher overall voltage gain while maintaining independent DC biasing through RC coupling.
In LT-SPICE, the MOSFET use Kp instead of K. The relationship is that K is equal to half of Kp because we assume the W over L ratio is 1. So to get a K value of 1 milliamp per volt squared, we simply set Kp to 2 milliamp per volt squared.
Voltage with a 10 mV peak and treated at a mid-band frequency of 1 kHz along with an AC square amplitude of 10 mV. To run the multiple analyzers required for this project, we added dedicated SPICE commands including .op for DC bias, .trend for transient analysis, and .ac for frequency response gain. Next, let's look at the simulation waveform result. For the transient analysis, the plot clearly shows the final amplifier output signal across the lot in green. With a 10 mV peak input, the output reaches approximately 18.6 mV peak, showing successful amplification. Most importantly, the output wave is perfectly smooth without any clipping distortion, and it is completely in phase with the input signal, and the two inverting stages cancel each other out. Finally, the AC frequency response plot confirmed that the core amplifier gain measured as V out over V in is stable at 5.81 dB in the mid-band frequency range. This translates to a linear gain of 1.95. When considering the 600 ohm source internal resistance, the total systemic voltage gain from VSIG to the lot becomes 5.4 dB, which perfectly matches our transient waveform result of an 18.6 mV peak output. This clear distinction between amplifier gain and total systemic gain successfully validates our complete design. This provides clear validation that our amplifier operates perfectly within the designated frequency range.
So, based on the requirement, I will explain the AC gain calculation, starting for the output side. The common emitter stage 2 has a AC lot consisting of the collector resistance in parallel with the 20k ohm output lot. Factoring in emitter degeneration, we calculate the stage 2 voltage gain AV2 to be negative 1.92. Moving to the common source stage 1, its AC lot is heavily influenced by the input impedance of stage 2. By calculating the impedance and using MOSFET transconductance, we determine the step 1 voltage gain AV1 to be negative 7.98. To find the overall system gain, we must verify that it is the product of the individual stage gain. We multiply the AV1 and AV2, and importantly, we must account for the input signal actuation caused by the 600 ohm source resistor. This gives us a theoretical total gain of 40.97. Therefore, a 10 mV peak input, our theoretical output is 149.7 mV peak, as shown in our waveform. The simulation result closely match this. Any minor deviation are completely normal and are due to the complex internal SPICE parameter of the transistor model. Thank you.